Okay, great. Yeah, thanks for the introduction. So my name's Teal Pershing, and was already introduced that I'm going to be talking about some of the time projection chamber research and development that we're doing at Livermore, specifically in support of trying to push the sensitivity further on dark matter searches in large monolithic TPC detectors. Okay, go. Okay, so here's a talk outline. Give just a little bit about me, and then just talk just very briefly about the group, and I'm going to talk more about the research that the group is doing later as well. And then, so I'm gonna the kind of the idea for the scope of this talk is I'm gonna start with big and then move my way in. So I'm gonna initially just talk about the motivation for dark matter, specifically weakly interacting massive particle dark matter. And then I'm going to give some context for at sort of the state of the art, large scale TPC detectors for dark matter searches, kind of where and how these searches are done, what technologies are used, where they're chosen to be done, and why. And I'll be talking specifically about the LZ experiment as an example, because Livermore is a collaborator on this experiment. And then from there, we'll start narrowing into the research that's being done at Livermore for improving WIMP searches in detectors such as the LZ experiment, but just broadly on the whole for dark matter searches. And I'll talk about some of the specific work that we've done and how it's led to projects that are going to be coming up this summer with our smaller xenon TPC and also xenon doped argon TPCs that we have here on site. Okay, so first, just a little bit about me. So I'm a staff scientist at Lawrence Livermore National Laboratory, but I completed my Bachelor of Science in Physics at Oregon State University in 2013. And then I got my PhD in physics at University of California, Davis in 2020, mostly specializing in detector construction, calibration, and then also analysis, but for neutrino detectors. So another sort of rare event detection search, adjacent to some of the technologies used for dark matter. But then when I started a postdoc at Livermore, I moved into detector assembly operation and data analysis, specifically more for dark matter. But in the rare event detection group at Livermore, we also do have some additional neutrino physics that's done. But I've started to use my skill set as a staff scientist hired on at Livermore to also work in applications of particle detection for nuclear safeguards and arms control. My hobbies, I like walking my dogs with my wife, who's shown over on the right. Charlie is the dog in the middle picture, and then Poncho's on the bottom left. Also like to travel. Went to Tokyo last year and try to go to China at least every year, every other year with Annabelle. I've been starting to do aquascapes recently. It's very hard, and I'm not very good at it, but there's a picture of a small one that I've worked on. And then also pottery, which is also very hard, and I'm also not very good at, but I have a few cups and pots that Annabelle and I have started making here in the bottom right. So now, just to talk a little bit about the Noble Liquid Group at Livermore, which I'm a part of. So largely, as I said, we have a research emphasis on xenon and argon-based rare event detectors, which I'm going to talk quite a bit about, those technologies through the rest of this talk. But we mostly have applications in this group, specifically in dark matter searches, neutrino physics, and then also nuclear safeguards applications, particularly when it comes to measuring neutrino fluxes from reactors or generally sort of very high rate radioactive sources. And then our group is a mixture of graduate students, postdocs, and research scientists. So I think something to keep in mind as you're sort of moving through your physics career, if you continue beyond undergrad, is that there's sort of opportunities at multiple levels to be able to sort of join or try and get involved in the rare event detection group at Livermore as well. This is a picture of a larger portion of our group. James Kingston is in the middle. He's a graduate student. Rachel Menino is a postdoc who is becoming staff. And then Ethan Bernard and Jinka Shu on the right are research scientists with Jinka as the main PI. Okay, so now I'm going to start talking about some of the background and some of the context. So first, I'm just going to talk a little bit about generally dark matter in our universe. Why do we care? Why are we sort of on the hunt for dark matter? So the amount of regular matter in the universe is pretty vast. So observations suggest 100 billion galaxies plus in our universe, so a huge amount of matter. But based on observations that have been made in astronomy and then also cosmology, it's expected that this is really only a fraction of the matter in our universe, where there's actually several times more matter in the form of so-called dark matter. And then there's this other even larger portion of dark energy, but what I'm going to really focus on today is the dark matter portion, or sort of the physical matter that is called dark essentially because it's some matter that doesn't participate in electromagnetic interactions. So in practice, it doesn't absorb, emit, or reflect light, so we can't see it. But it is there. So what is some of the evidence for dark matter and why it's postulated we have this non-luminous matter in the universe? So if we go to the next slide, there's sort of several examples in astronomy and cosmology, but I like to talk about these two because I think they're um, some of the sort of earlier and more prominent ones, but also sort of, I think, like pretty like visually strong. So one example is if you look, observations of the rotational speed of objects in galaxies throughout the universe. A very large portion of these galaxies, the if you take up all of the visible galactic components, so if you focus in this bottom plot on the left, these two curves, the disk and the gas, for a single example galaxy, and you try and model with the sort of total mass and gravitational, what we know as sort of classic gravitation and Kepler's laws, the velocity of the luminous matter as a function of radius does not match, it's not consistent at all with the data as observed, which are the dots in this plot on the bottom left. But if you have some additional mass component, which is not able to be seen with telescopes, is just there and it's dark, you can use that to sort of make up and explain the missing amount of mass to get a model that agrees with rotational velocity as a function of radius. A second example is in the reconstruction of mass density profiles for larger objects in the universe using gravitational lensing. So an example of this in the bottom right is the bullet cluster. And so, gravitational lensing tends to sort of bend and warp light that travels to us from objects. And what you can do is you can look at a cluster of galaxies, and the gravitational lensing can be used to try and reconstruct where the majority of the mass that's doing this lensing is. And so in the case of the picture in the bullet cluster in the bottom right, that's the blue cloud. And then the sort of expected mass profile from the visible luminous matter, this hot gas X-ray emission, is in the pink. And you can see those two do not overlay at all. So there needs to be some mass component that you just can't see to explain the gravitational lensing profile. So these are just a couple examples, but hopefully pretty strong ones to convince you there's some other mass out there that we need to try and explain and understand. So as far as what is the fundamental nature of dark matter, how does it potentially interact with standard matter? The interaction mechanism at this point is sort of still a mystery, and it's something that we're hoping to discover, and a lot of different kinds of experiments and different models are being tested. But a few things for all of these sort of need to be true and can help to constrain how you're going to try and search for dark matter. So we know that it needs to be uncharged because it's dark, it's neutral, doesn't interact through electromagnetic interactions, but it does need to interact gravitationally to explain what we saw in the previous slide. The abundance observed in the universe now needs to agree ultimately with different cosmological observations and models and data that's been taken as well. And the particle needs to be stable because ultimately that sort of amount of dark matter that we have now isn't drastically changing from what we've been able to see up to this point. So that it should be stable and have a lifetime sort of much larger than the age of the universe. Now, one possible dark matter candidate, and a strong one motivated by the so-called WIMP miracle, is weakly interacting massive particles, or WIMPs. And so WIMPs would essentially be a massive dark matter particle, which would have some additional small weak interaction with standard matter, and it would allow for the detection of dark matter directly in particle detectors. So in the bottom left, you'd have dark matter coming in, interacting with some kind of standard matter. There would be some beyond standard model physics that allows that interaction to happen, and potentially some energy would be departed to the standard matter, and you could detect the dark matter interaction with that. So under this kind of model, the WIMP search methodology, really how it goes and how it's commonly sort of executed these days, is what you do is you try and take a detector and you build a detector that's hopefully large, with a very large target volume to have dark matter try and interact with it. you design it with world-leading low background rates, so there's not much other particle interactions going on in your detector. Ideally, it's a very quiet sort of detector relatively, as far as event rates go. And then you search for signals in that detector that are unexplainable by the standard model. So there's sort of there needs to be, you look for a bump, so to say, or something beyond standard model physics. And so that's kind of how these searches go. And I'm going to now talk about where these searches tend to be done and how they're done, particularly using LZ as an example. So the LZ experiment is conducted in Leeds, South Dakota, and the primary reason for this is that these detectors, you don't necessarily want to just build them on the surface. You need to actually build them underground. And the reason for that is because if you try and make one of these detectors on the surface, cosmic particles are constantly raining down on us, and they'll produce very large backgrounds. So this is definitely not going to be a quiet detector that you're going to just be searching for WIMP searches once in a while, because there's just too much going on from the cosmic particles scattering inside of it. So instead, the detector gets built oftentimes underground, and cities that have a mine that already has access to deep underground is oftentimes a very good choice for a place to build a science lab and put a detector like this, so you don't have to dig yourself a mile underground with your own science funds. That's already done for you. So I've got a couple of photos of kind of what this actually looks like. Let's see, hopefully these videos will actually work. So if you want to, let's see, is that going to start? You gonna go? Come on, buddy. There we go. So this is, if you want to actually get down to the lab, this one is actually sort of at the end of the workday going up, but you need to take a cage, which is used by the mine workers to go down to different levels and do their mining excavations. But scientists will also use them as well to get to the lab at whatever level they're at. You'll sometimes need to walk your way down to this lab as well. And then after you've finished your day, if you're lucky, you'll maybe get to ride in a mine cart, depending on what lab you're in. This was pretty fun that we actually got the chance to do this on one of my first trips when we went down to surf. Surf being Sanford Underground Research Facility. Okay, so we've got a location that has low background rates. Now we need a detector that can have large volume and be very sensitive to dark matter interactions. So the state-of-the-art detector technology right now for doing weakly interacting massive particle dark matter searches is the time projection chamber. So oftentimes I'm going to probably talk in the context of a TPC that's specifically using xenon as its detection medium. But for now, I'm going to kind of just try and keep it general for this explanation. So time projection chambers, the way that they work is, first, if you want to detect a particle interaction, you need some target volume for the particle to scatter with that you would detect the interaction with. And so in this case, you use a large volume of xenon in the case of the LZ experiment, and you fill it into some cryostat, which is going to be this sort of blue figure that we see here. Now, you then need to be able to actually detect particle interactions that when they happen and occur on the xenon. So let's say you have some particle, in this case, we hope it's a dark matter particle, and it scatters with a xenon nucleus. Well, when it scatters in xenon, it imparts energy into it, and then that xenon will produce a visible signature that could help you indicate that particle interaction happened through a couple different de-excitation modes. So if we look at the plot on the bottom right, there's two main ways that you can see that energy deposition. So one is through scintillation, or photons that end up being immediately produced from the interaction. And the second is through ionization, where the xenon nucleus moves through other xenon nuclei and can ionize electrons. So we want to be able to detect both of those components of the signal. And so the S1, or the scintillation signal, so-called, you can detect that immediately by having really, really sensitive, so what are photodetectors to detect those sort of single photons. And so the top and bottom circles of this detector are all photomultiplier tubes, which are sensitive. They're photodetectors that are sensitive to single photons, and you can use those to detect those scintillation photons. Now, to then collect the second component of the signal to really maximize your sensitivity, those ionization electrons, you apply an electric field across the xenon, and those will drift up to the top of your TPC. And once they get from the liquid to gas interface, if you have a very, very strong electric field here, you can get this rapid acceleration through the gas and produce an avalanche of additional photons to give you a second scintillation signal, the S2. And so the S1 tends to be small, the S2 tends to be much larger. The time difference between those tells you where in the depth of the detector the interaction happened. And then you can use the total amount of light that's seen in the S1 and the S2 to reconstruct the energy and actually use the top array almost as like a camera with a bunch of pixels of photomultiplier tubes to reconstruct the position where the interaction happened. So this is kind of the cornerstone of dual phase time projection chambers for particle detection. And this top right plot just shows you an example of how this looks in actual data in one of our smaller TPCs. In this case, there was a double scatter, so we actually see two S2s at different times because they happened at different depths in the TPC. So this is what LZ uses, and this is what we're going to be talking about for the most of this for the rest of this talk as the technology for WIMP searches. So why use the TPC versus other particle detectors for dark matter searches? So I'd say two larger reasons for this. A first one is that these detectors have down to low energies, very good discrimination between something that looks like an electron moving through xenon versus something that looks like a nucleus or a xenon nucleus, a nuclear recoil in xenon. So the dark matter, primarily the main channel of detection is dark matter particle scatters on your nucleus and then will sort of it'll impart some energy to that nucleus, which can then transfer energy to the rest of the xenon and also create your scintillation and ionization. You want to be able to discriminate that from other dominant backgrounds that oftentimes are gamma rays scattering in and potentially scattering off these electrons, for example. And so that looks distinctly different. If we look in the plot in the bottom right, this gives an example of the sort of really strong electron recoil, nuclear recoil discrimination. So the orange band here are nuclear recoils from a neutron source that are produced in the LZ detector. And the blue are electron recoils that come from another calibration source known as tritium in the detector. And you can see that you can clearly tell the difference between those, which you really want to if you want to be able to really isolate down to just your nuclear recoil and ideally, hopefully, dark matter scatters in your detector. This plot space, just for reference, this x-axis, again, this is your scintillation, your S1 signal, and then the y-axis is your S2, that's your ionization signal, and it's the difference in the ratio of those two effectively that lets you identify those nuclear recoils. You can also see that the sensitivity for separating these two signals is very good down to low energies, down to just a couple keV in the case of electrons and nuclear recoils. And this is pretty valuable sensitivity when it comes to looking to sort of smaller energy scatters from what's expected to be a pretty weak signal from a WIMP scatter in xenon. Okay, so now I'm going to talk more about kind of at the sort of high level the LZ experiment just briefly, and then I'll start moving into LZ and how we're the Livermore group and how we're enabling larger detectors like the LZ experiment. So the LZ experiment, which is in Sanford Underground Research Facility, has 7 tons of liquid xenon to do that dark matter detection. So the picture on the right shows that time projection chamber main volume. So the xenon would sit inside of this white, tightly wrapped space. And then you can see those photomultiplier tubes on the bottom and top for reconstructing those particle interactions that happen in the TPC as well. And this is so pretty large volume that we're using to try and detect and do those dark matter searches. And then the picture on the left just shows that outer cryostat, which keeps the whole thing outside of this cryostat under vacuum because you got to get xenon down to liquid, you need to keep it at around the order of 180 Kelvin, so quite cold. So where is the field at right now as far as sensitivity to dark matter? So LZ currently has the world-leading sensitivity when it comes to xenon time projection chambers and searching for WIMP dark matter searches. And generally how a search is done is if you look at the plot on the bottom left, this is a similar plot to we saw earlier with that calibration data where the x-axis is your effectively number of photons from that S1, and the y-axis is that number of ionization electrons, effectively the S2. And you can see after applying a bunch of data quality cuts to really clean up the data that there's a large amount of events in this gray band from electron recoils. So it's pretty well separated from the purple region, which is the model that predicts where you would expect to see your WIMP signal. And so from there, you can compare the model to what you see experimentally to see if there is any beyond standard model physics more events than is just predicted by your backgrounds. In the case of LZ, the data was consistent with expected backgrounds. So then LZ then goes to setting a sensitivity limit, which is the plot on the bottom right. And these sensitivity limits are usually excluding regions of cross section, or essentially, strength of interaction between WIMP and some nucleon, in this case xenon in your TPC. So the x-axis is for some WIMP mass, you can rule out some kind of strength of WIMP nucleon where, oh, if the strength of interaction was stronger than this, LZ would have seen it to some level. So the black curve just below that green curve shows you kind of where the current limit is right now. This is from an archive publication, and it's being submitted to PRL, and that's an in progress publication. So I know that's quite a bit, but we're going to start to narrow in now. And the reason I kind of wanted to show this plot is that it really sort of drives the motivation for why we want to do additional smaller scale measurements with xenon TPCs at Livermore. And that's primarily to take this sensitivity curve and enable detectors to try and push this curve lower down and be able to exclude stronger regions of sensitivity space. So let's first talk about generally, how can you continue to push the frontier of dark matter sensitivity? We need to think about how would we go about trying to improve and continue to get stronger limits on dark matter searches. So one thing you can do is you can continue to just take more data over time. So if you have more data, more statistics, you'd have more time to be able to try and measure that dark matter, and that's just overall going to improve your sensitivity. Fortunately, eventually the cost of running versus improvements in that sensitivity just has diminishing returns. So then usually several options for more considerable improvement will generally be taken by the field. So first, you can just make it bigger. You can make a sort of a next generation dark matter TPC, which there is discussions of a detector called XLZD, which would be an even larger xenon volume than the current LZ experiment and the current xenon and Ton and Darwin experiments that are kind of the sort of at the forefront of xenon TPC searches. You could also, though, work on just trying to improve your analyses. So instead of trying to make changes to the detector as it runs, you can just try and reduce the uncertainties and improve your understanding of the fundamental physics that can end up sort of leading to uncertainties in the measurement that you set. For example, trying to have a better understanding of what is the expected S1 and S2 signal for nuclear recoils at some energy. The better you understand that, the better your event reconstruction, and it just reduces the uncertainties in your experiment. Another thing you can do is you can also just try, without making the detector necessarily bigger, but you can just generally try to improve the technologies that you're using to provide better sensitivity to a particle signal of interest. So instead of using photomultiplier tubes, maybe you use a different, better kind of photodetector, or you just upgrade your photomultiplier tubes for doing that event reconstruction. These kinds of things that you can try and do. So at Livermore, we're specifically going to be talking about today our results and work that we're moving forward that kind of target the second and third points here, really trying to reduce or get a better understanding of fundamental nuclear recoil physics, and then also just improving the technologies that we can use to do dark matter searches. And these particularly will have a pretty strong impact at kind of, with the measurements done at Livermore, at the fringes of this sensitivity region. So really low WIMP mass, where the energies that you expect to see deposited in your detector are kind of on the smaller side, and then larger WIMP masses where you kind of have larger scattering and larger energies just with the kinematics of it. So this is really where we're hoping to kind of, in some ways, flatten this curve to get better sensitivity to dark matter at the edges and enable detectors to sort of have that capability. Okay, so now I'm going to start zoning in and really talking about work that's going on at Livermore. So there have been, over the course of the last decade or so, quite a few measurements made at Livermore to enable and improve the understanding of nuclear recoils in xenon TPCs. I've listed for publications here with the archive references, so you don't need to have any kind of a paywall or anything to go and look at these. But I'm going to focus primarily today on the two most recent measurements that were made and talk about them at a high level. So measuring light and charge yield, effectively the S1 and S2 of higher energy neutron xenon scatters. And then I'll also talk about a search for what's called the Migdal interaction using neutron xenon scatters. And I'll talk more about that in a few slides. And the main reason here is I'm going to talk about these measurements and how things that were observed or not observed will lead to the next measurements that are going to be coming down the line for us in our group. So first, I want to talk about the Xenon TPC that we have at Livermore and the technologies that we're using to try and make some of these fundamental measurements. So we need a Xenon TPC if we're going to be trying to do TPC measurements. And so the Xenu detector is the detector that we have at Livermore. It was designed and constructed here in-house. I've listed some of the details of the technologies, but I think the main thing I want you to focus on for a moment are just sort of the pictures in the top right. You can see that this is effectively a TPC that has all of the same components as what I had talked about earlier and what's in LZ, just at a smaller scale. So we have, instead of having 500 photomultiplier tubes to do really good high granularity event reconstruction, we have 4 smaller top PMTs currently that see that S1 and S2, and then we have one larger bottom PMT at the bottom to help collect as much of the light as possible. We also have extraction grids that provide the electric field needed to drift those ionization electrons. And we have about 150 grams of active xenon that are sort of inside this main detection region where that electric field is. So a picture of this in person is on the right. You can see Jinko working on this, and it's just about the size of a person's head, so much smaller than what you see in LZ, but it does allow us to be able to perform multiple experiments, multiple cool downs at higher rates, not having to work with 7 tons of liquid xenon. Instead, we've just got a smaller amount. And we can get this detector up and running and decommissioned if we need to make modifications, in the course of days to weeks rather than months to years. So this is the main detection region for xenon TPCs. Now, for understanding xenon interactions, we also need some kind of a nuclear recoil source. Now, we can't make a dark matter source to make nuclear recoils happen inside of our TPC. So instead, what we do is we use neutrons effectively as a proxy for nuclear recoils that they would look very consistent with some kind of a WIMP dark matter scatter. So if you look at this picture on the right, instead of dark matter scattering on your nucleus, it's just a neutron that's a neutrally charged particle that scatters off of it. So we have the facilities to be able to make collimated neutron beams directed towards our xenon TPC. So we can use 2 energies pretty readily. So we can use a lower energy neutron or a higher energy neutron, depending on what kind of measurement the requirements call for. If we're focusing on a lower energy neutron range or a higher energy nuclear recoil range. Now, we take that neutron source and we put it inside of a large water shield. So you can see that in this sort of back right picture, and the sort of bottom right, you can see it in the back there. And then collimate the neutrons using a bunch of borated plastic and direct them at the xenon TPC. In the picture on the bottom right, the metal can that's right there in the middle of all of those detectors is where that xenon TPC is. There are then backing detectors, which are just liquid scintillator detectors, placed at different angles around the TPC. And what we can do is use the coincidence of neutron scattering in xenon and then scattering at a second detector and use that angle with just simple particle scattering kinematics to say, oh, for that signal in the xenon TPC, we know it imparted that much energy because we saw that it scattered at that angle. So this allows us to make precise measurements of xenon's nuclear recoil response at different scattering energies. Now, I mentioned earlier that a measurement that was done recently where we wanted to look at that S1 and S2, that light and ionization signal, as a function of scattering energy. And we used a DT source to do this in xenon and make measurements at different field strengths inside of the TPC. So the measurement for that was successful. We published in PRD. The data for that is on the bottom left. I'm not going to talk too much about it, but the green, red, and blue dots sort of show the points that we measured, and then those lines are the sort of simulation known as NEST that it compares against, and we're in relatively decent agreement, in particular in the charge yield region. But what I mostly want to focus on is that there was an interesting side effect from this measurement that we saw, which was that at our higher energy scatters that we were trying to measure this light and charge yield in, we found that the counting statistics were much lower than we expected. In this case, some of them at the highest energy points were lowered by up to almost an order of magnitude lower than what we were anticipating. And so this led to an idea of, well, why is there such a big discrepancy here? And if you look more into the theoretical predictions at these higher energies, most of them are strictly based on models. There isn't actually data there to be done, to be added in and compared to the theoretical prediction. So something that we're doing right now at Livermore is we're setting up to essentially use the same setup that we did with this light and charge yield measurement for these energy scatters, but instead refine our setup and refine our analysis to instead focus on trying to measure the neutron xenon scattering cross section. So you can see that we're still using these backing detectors around at the bottom left, around the xenon TPC to measure the number of scatters at different angles, and ultimately we'll be able to make a plot like on the bottom right here, where we compare some data points to the theoretical predictions for what is the neutron xenon scattering cross section as a function of scattering angle. These red dots give an estimate of a rough approximation of what we saw with some of our first measurement and the discrepancies that we expected, but we do still need to refine our analysis and make sure we put some good error bars here, and really focus in on understanding our analysis and our efficiencies, to make sure that we get a good comparison to the theoretical data. So this is coming up right now for our group. Uh, so the second thing I'd like to talk about, a measurement that's going on with our xenon TPCs coming up, is a continued search for what's called the Migdal effect. And so this is just a real quick background on what is the Migdal effect and what is its impact for WIMP dark matter searches. So the Migdal effect is an effect that's a predicted phenomena for these low energy nuclear recoils, which in this case could be, very low mass dark matter that gives a pretty weak recoil on a nucleus. So the idea for this effect is if we look at this figure on the bottom left, you could have some kind of dark matter particle come in and scatter off your nucleus, as we've been talking about throughout this talk. But if it's a really low energy scatter, maybe it's a really light mass dark matter, or it's just not very high velocity, then the nucleus will only slightly be displaced from sort of its base electron cloud. And then the energy that would be below a detection threshold, it just won't produce, ionization electrons or scintillation photons for you to be able to efficiently see in your detector. But if the Migdal effect occurs, what will happen is once this nucleus is displaced, the electron cloud will essentially try and snap back to come back to its original location around the nucleus. And this displacement has a non-zero probability of an electron being kicked off in some excited state with some kinetic energy. And potentially that electron's energy as it moves through xenon could be above the energy detection threshold. So for WIMP dark matter, you're taking low energy WIMP scatters that are nuclear recoils, which you couldn't see, and hoping that you can see them as a low energy electron signal. And if you can verify its existence, this would help you to do different kinds of WIMP searches that can lead to stronger limits in sort of particular models of WIMP searches that you're trying to search for. So we set up an experiment at Livermore to try and measure the Migdal interaction in our small xenon TPC. So we use a similar kind of setup that I showed for the light and charge yield measurement, but instead of having backing detectors at a bunch of different angles, you can see in this picture on the bottom left, all the backing detectors are instead put at a single angle so that you can tag neutron xenon scatters that should be at an energy where the Migdal effect is expected to be at a pretty high event rate. So you're trying to kind of optimize for looking for Migdal effect scatters in xenon. And the data from that analysis are shown on the right in the plot. And what you can see is the data are the black dots. The solid lines are all different components of the model for the signal. And then the Migdal effect predicted rates are in the dotted line in red. And you can see around that 100 to 150 electrons in the S2 signal, there's definitely a discrepancy between the Migdal predicted model and the actual data. So the data is below where the Migdal effect was expected to be, and there are current theories that are being worked on as far as why this would be the case, in particular in sort of the microphysics of the Migdal effect. But generally, on the hardware side and experimental side in our lab, we're really just trying to say, okay, let's see if we can improve and improve our sensitivity to sort of push this limit further and see if we can eventually actually see a Migdal signature, or see some excess above the baseline physics that we kind of expect to see with neutron xenon scatters. So to really narrow in on particular, just to give you an example of one thing that we know we're going to do to try and improve both of these measurements for upgrading our detector, is to effectively upgrade the, again, if you think of the top array as a camera for detecting these single photons and reconstructing where these positions happen, effectively upgrading the pixelation of that, the granularity and the resolution of it. So previously we had 4 photomultiplier tubes. What we've done already is we've moved to a 9-channel SIPM array, where if you look in this bottom middle picture, there's Hamamatsu SIPMs that you can buy commercially, where we're just ganging up the signal outputs from each of those 6 by 6 millimeter cells into one channel. So the red boxes kind of represent this is a single effective photodetector. These are also photosensors that are sensitive to single photoelectrons. They're just in a smaller package than photomultiplier tubes, and they do have some other different physics. Their pulses look a bit different. The picture on the bottom left are some example of single photoelectron pulses that you can see. This pulse on the left is probably several photons actually, but that the pulse that's kind of on the right side of that plot is probably a single photoelectron. So this has already been installed, and we've been doing some initial commissioning. And you can see Jinka here working with the TPC, prepping it for a cool down with the silicon photomultipliers. And all those cables kind of coming out of the top of it in that picture on the right is just where the SIPMs are at. But what we're planning on doing this summer is pushing it even further. And instead of reading out from 4 of these SIPM cells as one channel, we want to read out from every single one of those sort of mirrored silicon photomultiplier pixels. So a board has been designed for this readout already, and has actually been constructed as well. I just recently put it together after doing the design and modification for it. And the next steps are going to be plugging in silicon photomultipliers and really trying to understand the how different each of those SIPM cells perform from each other, just understanding and characterizing them. So, how different is their light collection efficiency? Essentially, you need to, again, if we're thinking of this as, a camera for reconstructing where particles interact, we need to know the behavior of each of those pixels. How good are they at actually collecting the light? And what's the optimal powered voltage to run them at to really be able to reconstruct those particle interactions effectively. So that's definitely a big project that's going to be coming down the line for us for the xenon TPCs, aside from just the larger setup of our detectors. So I see I'm running out of time. I have just a couple more slides. I want to talk about one other project that's ongoing in the group as well, that is adjacent to xenon TPCs, but a little bit different. So first, I want to talk about, I've been talking about xenon-filled time projection chambers, but xenon is not actually the only choice of noble element or even material that you can use for TPCs. Another choice that's also done for some dark matter searches that are ongoing, and also some other different types of particle searches, is argon. Argon is another choice that you can do as well. It has its own benefits and its drawbacks depending on what context you're using it for. One of its biggest benefits is that argon is a lower mass than xenon. So what that means is it can be kinematically favorable, as far as if you think of the simple particle scatter, WIMP scatters off of some kind of particle in a detector. Argon's a lower mass than xenon, so you can, on average, have more energy imparted to it. If you just think of like billiard balls kind of scattering into each other versus a ping pong ball scattering into a bowling ball. So an example of this is in the plot on the right, although this isn't for dark matter, it's for neutrinos scattering off the nuclei of argon versus xenon. You can see in this sort of model development of the expected average recoil energy for neutrinos from a reactor. that argon on average sees a larger recoil energy than the xenon. That's just due to the mass being smaller, so more energy can be imparted into it. Now, there are other drawbacks to using argon that you have to deal with, though. In particular, practically in the detector context, some of the big ones are the scintillation is a shorter wavelength, and this makes it harder to detect directly with commercially available sensors. The wavelength's on the order of 115 nanometers, and visible, of course, being in the 300 to 700 nanometers. They're challenging to build photosensors in that kind of short wavelength range. Uh, Scintillation emission time is also lower. So if you think of that S1 for reconstructing when the particle interacts, the emission time being slower, it's a more spread pulse. So you just don't have as good of timing resolution on the S1. But if you dope a small amount of xenon into argon, it actually provides the best of both worlds. You can actually get that lower mass primarily for the target, but you can also get scintillation light and scintillation emission time that's kind of more like xenon. But it is challenging to keep the xenon from freezing out of the argon in this case. So making a stable detector is kind of key. And we've developed a entire test bed for doing xenon doped argon detector testing at Livermore. So I have a few pictures here. In the middle picture, you can see, again, this is very TPC-like. You've got these grids for applying electric field to drift electrons. We have different types of photosensors, particularly SIPMs in the picture on the left at the top array to detect that S1 and S2 from the TPC signature. And this entire TPC is also put into a cryostat where we can really readily control the temperature and pressure and also the amount of xenon in argon. So we can actually control all these parameters and try and understand the performance of the detector in different configurations. And the something this detector is actually being ran right now as I speak over in the lab by a couple of our graduate students that are here who have been kind of leading the charge on a lot of this work recently. And the bottom left just shows some pictures of stability tests. There's a camera pointing into that TPC, and you can see that if you set your detector parameters, your temperature and your pressure incorrectly, you can have xenon ice, that's xenon that's in the argon, just start to freeze out on the edge of the liquid argon interface. But then if you change your detector parameters to somewhere where you get more stable mixture, we're able to have several days, and we can have longer actually, of having xenon doped in argon successfully. The picture on the bottom right just shows that with those SIPMs that we have, we're also doing measurements of what is the signal response, how much S1 and S2 light, in this case it's S2 in this plot, do we see as we change the xenon light? And so we're also doing analysis on data that's being taken right now to just understand the detector response for different xenon dopings. So that's the end of my talk. I know that was a lot of information pretty fast, but I hope it was kind of interesting. And if you have any questions at this point, I'm happy to take them. And I think I'll kind of just leave this here. We definitely have a lot of activity going on coming up in the next year to sort of prep for these measurements on both the pure xenon and xenon doped argon side. So yeah, thanks for your time. Yes. Let me see this one right here. Yeah. Mm-hmm. Yep. Yes, in particular, yes, and again, these just to note, these red triangles, they're not fully quantitative with like full uncertainties estimated. We sort of have a first order estimate though of at the very least we were definitely seeing rates suppressed to this level, and we want to now go back and measure them quite accurately. Right. Yeah, so one thing we are talking about doing as well is kind of like you're saying. So in this picture, you can see that the picture on the bottom left, the backing detectors are pretty large, and once you get to larger angles, it translates to an uncertainty on what was the scattering angle of the neutron because they have to get close to the TPC for you to have higher event rates. But then that also means that you're just effectively covering a larger angle. So something we've been talking about doing as part of the upgrades for this is uh, trying to move to smaller liquid scintillation volumes that are coupled to smaller PMTs or SIPMs that you could then instead of having just maybe one of those detectors, like you said, maybe you could take three of them or five of them, depending on how much we're able to get, and sort of putting them up vertically in space. So you're still getting a similar amount of backing detector volume, but you're able to still have good angular resolution. So that is something that we're talking about trying to acquire smaller detectors for doing at these high angles, especially. Yeah.
Actually, yeah, I don't, what was the aqua thing that you said was your hobby?
Oh, aquascaping? Yeah, yeah. I mean, it's essentially just trying to make like small tanks where you focus on like you focus on different combinations of plants and hardscape that just give you like a fun tank to take care of. I have one that also has fish, although the one I pictured, it's literally just plants and I just kind of focus on that. Um, so yeah. I guess it's almost like having house plants, but instead they're underwater.
Cool, thanks.
Yeah. No, no. Mhm. So not it depends. It depends on if things are going well or if they aren't. But on broadly, like if everything is sort of running optimally, usually this starts with before we actually put in the xenon and try and cool everything down, we'll start by just pumping out all of the other, spaces that are peripheral to the xenon. And that takes usually on the order of about a day to start the pumping, but then we'll leave it over the weekend to really get a good vacuum jacket around where the xenon TPC is on the inside. And then from there, cooling down the detector by moving cool xenon gas through it, and then eventually condensing it to get 150 grams of liquid xenon on our target takes on the order of a day or two. So it actually is pretty fast for us to get to a place where we're now at a point where we can start turning on our electric fields and starting to potentially see particle interactions too. Now, for the most part, we do have we have a slow control system that we're able to access remotely as well. So this is a system that measures the temperature and pressure at different places, and we actually have some automated scripts in place that will slightly vary temperatures and pressures to kind of keep the entire detector stable automatically. So we don't have to be watching the detector 24/7, but we do kind of need to at least be intermittently checking it, a couple times a day to make sure that nothing has gone wrong. Maybe like a pipe ended up actually, like creating a leak or something, and then our vacuum got bad, and that'll warm the detector up. Something like that, where it's sort of an off normal condition. But when those don't happen, we're usually checking things a couple times a day, and we usually are doing, for the most part, most of our measurements, in particular running neutron sources, is just in regular working hours because we don't want to be using, radioactive generating devices in off hours when there isn't necessarily help from like ESNH, for example, environmental safe health and safety. So. Mhm. Yeah, we're a very like hardware driven group, although we do have some opportunities for doing simulation analysis as well. There's a lot of opportunities for hands-on experience here, especially right now as we're preparing and setting up for our next round of measurements. So, yep, that'd be great. Yep. Thank you for having me. Appreciate it.